So let's start to talk about the phoneme analysis. So for stability, it is another approach to show the stability of the method for partial differential equations. So in the past approach, what we did was to transform the partial differential equation using the method of lines into a ODE system, and by knowing the properties for the eigenvalues for the matrix of this system, we restricted its absolute value to be smaller than 1. So it depends on knowing how the eigenvalues of this matrix looks like. Here is a more general approach. So in the von Neumann approach is based on the Fourier analysis, and usually it is applied to a Cauchy problem. So a Cauchy problem, it's a problem when in which we have x going from minus infinity and plus infinity in the 1D case. And we can use the Fourier transforms because of this property. So the derivative of an exponential function according to x, it will be given by this. So it is the function itself. So the function is this, okay? So it will be the function itself multiplied by IC, and the functions, these functions in this way with wave number c, where c are constants. They are eigenfunctions of the differential operator del x. So so it means that this function del x, it's equal some constant times f, okay? So when we apply this operator del x at the function f, we get some constant times the function f. So the von Neumann analysis is based on the fact that the related grid functions, given like this, they are an eigenfunction of any translation invariance operator. So the idea here is to transform our origin. So originally we have a problem in the real, in the continuous real number. So we transform this original problem into the Fourier space discrete. So we transform first the partial differential equation into its discrete form of using finite differences, and then we transform these discrete functions into the Fourier space, and then we use this property, okay? So suppose that this zero here, the operator d0, it's a differential operator, okay? So if we have so it's E, I, J, h psi. So this is just the discrete form of the function that we have seen before, which was I x psi. But now we are on the discrete grid, okay? So we are looking for x of j, in which x of j is j times h, for j going to 0, j going to from 0 until some number n. So if we apply the operator d0 here, which is a differential operator, so here we want to approximate the first derivative. So we can approximate this using the centered approximation, which is xj v of xj plus 1 minus v, I need more space, sorry. So v line of xj, it's equal v of xj, it's approximated by so v of x at j plus 1 minus v at xj minus 1 divided by 2h. And when we transform this function v evaluated at xj plus 1, so we would have at the Fourier space here I is square root of minus 1, is imaginary number, so I j plus 1 h psi. Okay, that's why we have this expression here. So so then what we do on the next step, we put on evidence the term depending on jh psi. Okay, so here we are going to have a minus. So this is the eigenfunction. So here we call it eigengrid function because now we are looking for the discrete. Okay, so we are in the discrete grid, and we know, so here is the eigengrid function, and here this term is equal this, so it's the because remember that EIH psi, it is equal cosine of H psi plus I sine of H psi, and the other E minus IH psi, it's equal cosine of H psi minus I sine of H psi. So when we sum both, So is the first one minus the second one, so minus this one. So here it will be a minus and here a plus. So if we sum the first with the second, we will get, so this term will cancel with this, so we get 2I sine of h psi. And then this 2 here will cancel with this other 2 here, and therefore we get that d0. So our Wj is given by this, so E ij h psi, it's equal this, okay? So it's equal I divided by h sine h psi times the eigengrid function. We say that Wj is an eigengrid function of the operator d0 with the eigenvalue given by this. So this is the constant. Remember, when we have our eigenvalue problems, is something like this. So V are the eigenvectors, and the constant here will be the eigenvalue. So in this case, here I divided by h sine of h psi will be the eigenvalue. So now suppose that we have a grid function v of j defined at grid points, x of j equal j times h. So j equal this, because we are on considering the Cauchy problem. So our continuous space is given by this. So when we look for discrete grid, we will have infinite points on both directions. So here L2 is a Banach sequence space based on the norm 2, in that sense of the 2 norm. So U here is a vector. So so we are considering that U is a vector, is a sequence, okay? So it's some sequence given by this, okay? And so on. So what we are saying here, that if we are on the space L2, this norm here is finite. So if this happens, then we can express Vj as a linear combination of the grid functions, okay, for all wave numbers c in this range. So our Vj is given by this. So we are just this is just the discrete Fourier transform, okay? So we are transforming point in function that was in the grid space here to the Fourier space, where this V hat is given by this. So this is the inverse Fourier transform. Okay. So why I'm saying that? Because now we are want to apply this to our numerical method. So after Fourier transforming the finite difference method, we obtain a recurrence relation for each U hat of psi, that is, it depends on the wave number psi, and that is decoupled from all wave numbers. It has this form. Okay. So now we are looking for our finite difference method in the Fourier space, and it has this form here, and this G of psi is called amplification factor for the method at wave number psi. If we can show that this amplification factor is bounded by 1 plus alpha k for some alphas constant that doesn't depend on psi, then the method is stable. So it comes from that theorem that we saw earlier from the Richtmeier stability theorem. Okay, so let's see some theorem that you can find it at the Levesque book. So one step finite difference scheme is stable in a stability region S if and only if there is a constant alpha such that this happens with K, H, and S at the stability region. This stability condition can be replaced with the restricted stability condition, so which is this one, and this theorem shows that to determine the stability of a finite difference scheme, we need to consider only the amplification factor G of psi of the method. So let's see some example. So earlier we showed that if we want to solve the diffusion equation, so del U del T equal in 1D del X square. Okay. Yeah, we have the diffusion coefficient. Okay, and then so we use this to approximate the Laplacian, and here we are using the forward Euler method to integrate on time. So we are considering this space-centered finite difference approximation with forward Euler time integration. So we from the earlier example that we saw through the method of lines, we got that the stability condition is dk divided by h square should be smaller than 1/2. Okay, so now we are going to use the von Neumann analysis to find the stability region for this stability condition for this method, and we expect to obtain the same result as before. Okay, so first we are going to write our method on the Fourier space. So we have this, and we also have this, and we just remember also that uj minus 1 at the time n, it will be equal e I j minus 1 h psi, and also for j plus 1 it will also be something like this, and then we get all of this and substituting the method here. So on the right hand side here we had un plus 1 I what happened? Okay, so here un plus 1 I, here u I n, u I minus 1 n, u I n, u I plus 1. Now we are putting on evidence the common terms, which is this one. If we look here, we have some sum. So E minus I h psi, it is equal cosine of h psi minus I sine of h psi, and e to I h psi, it's equal cosine of h psi plus I sine of h psi. And summing these both terms here, this cancel with this, and then we get 2 cosine of h psi. Okay, so this 2 is here, multiplying the cosine, and then this 2 also comes here. So we see that our amplification factor, the function g of psi, is given by this. Okay, and for having this restricted stability condition, we want to find for which conditions for the parameters k, h, and d we have this amplification factor smaller than 1. So just remember our g of psi is equal 1 plus 2 dk divided by h squared cosine of h psi minus 1. Okay, so remember that what we did before. So for having this is smaller than 1, it's the same to ask that this g of psi be between minus 1 and 1, and then we look for separately for this first condition, and then no, we look for the condition separatedly. So since cosine of psi h is between minus 1 and 1 for any, so here is the second condition. Okay, so for any psi and h, the condition 2 is satisfied, and then for the first condition it will be satisfied if this happens, and therefore we have this result, which is our stability condition. Okay. So as exercise, I want you to show that if we want to solve the diffusion, approximate the diffusion equation using the Crank-Mixon method, I want you to show that this method is unconditionally stable. So for that, let's look to each one of the terms. So in the Fourier space, you have that u and j, it will be e I j h psi, and then u n plus 1 j, it will be g of psi e I j h psi, and then this term u, so let's put j plus or minus 1 at n, it will be e I j plus or minus 1 h psi. And now these terms here. Okay, so this one we already determined, so these two here. Okay, so u n plus 1 j plus or minus 1, it will be g j, so you have the amplifying factor times e to the I times j plus or minus 1 times h and psi. So you substitute all these functions in so you transform the method to the Fourier space, and then you are going to find a equation for the amplifying factor, and then you need to show for which condition the absolute value of this amplifying factor is smaller than 1. So for the method to be unconditionally stable, you are going to see that it doesn't depend on h, k, or d. So for all h, k, and d, your amplifying factor will be smaller than 1. So that was it for today, and thank you, and see you all next week.